All right, we're going to dig into this fantastic editorial that asks a really pointed question. Where is the power in a power analysis? Now, it might sound super technical, but trust me, it gets right to the heart of how we trust scientific research. So let's just dive right in.
Okay, so first up, let's just tackle a huge assumption. You see a study, right? One has 20 people, the other has 200. You probably think, well, the one with 200 is obviously better. I mean, it just feels intuitive, doesn't it? More data has to be better. But what if I told you that's not always true?
See, a study isn't better just because it's bigger. It's better if it's actually designed correctly right from the get-go. And the absolute key to that design, you could say it's the engine that separates a good study from a totally wasteful one, is this thing called statistical power.
So, what is this thing, this crucial ingredient? Well, the easiest way to think about it is like this. A power analysis is the pre-flight check for any research study. I mean, you would never want a pilot to just guess if they have enough fuel, right? And in the same way, we really don't want researchers just guessing if they have enough data. And here's the critical part. A power analysis is a calculation that's done before a single person is recruited, before any data is collected. Its whole goal is to figure out the absolute minimum number of participants you need to have a fair shot at actually detecting an effect, assuming one really exists. It's all about being efficient and not wasting everyone's time and money.
But honestly, its purpose goes even deeper than that. For one, a good power analysis helps you plan the perfect sample size for your specific question. It also helps researchers avoid two, let's call them critical errors. There's the false positive, that's when you think you've found something, but it's not actually there. And then there's the false negative, where you completely miss a real effect that was right under your nose. And maybe most importantly, it's supposed to be a safeguard against some sketchy practices, like something called p-hacking, which is basically when a researcher just keeps twisting their analysis until they get a significant result they can publish.
Okay, so in theory, this all sounds perfect, right? But in practice, oh boy. This whole process can go wrong in some really interesting and, frankly, problematic ways. This is exactly where good intentions can end up leading to some really bad science. One of the absolute biggest issues is something called the file drawer problem. Just picture this. A researcher runs a perfect study. It's well-powered, everything is by the book, but the results are kind of boring. They just don't find anything significant. So what happens? The study gets shoved into a metaphorical file drawer and never sees the light of day. And here's the thing. That's a huge problem because it completely pollutes the scientific record. We end up only seeing the flashy, exciting positive results, which can make it seem like certain effects are way more common or real than they actually are.
And then there's an even more deliberate problem. The source we're looking at calls it power hacking. And this is basically when researchers aren't using the power analysis to plan their study. Instead, they're kind of working backward, manipulating the analysis to justify a sample size they already have, or, one they can actually afford.
This next slide just perfectly illustrates the difference. So with good practice, researchers look at past studies, they look at pilot data, and they make an honest estimate of the effect size they're looking for. But with bad practice, well, they might just inflate that number. They'll claim they're looking for a huge effect. And why would they do that? Simple. A bigger expected effect means you need a smaller sample size to find it. It makes the study cheaper, it makes it faster, but it also makes it way, way less reliable. And the problems can get even sneakier than that. A power analysis might look totally fine on paper, but it could be built on a really shaky foundation. For example, a researcher might say they based their calculation on a previous study, but they don't say which variable from that study they used. Or here's another one. They use data from beginner athletes to predict how elite athletes are going to perform, which of course is a totally flawed comparison. And the classic. They just throw in a 20% dropout rate for good measure, with absolutely zero evidence to back it up. All of these are ways to create the illusion of a rigorous study, without actually doing the hard work.
So with all these potential pitfalls, you've got to be wondering, who's supposed to be catching all this stuff? I mean, who are the gatekeepers here? Whose job is it to protect the quality of the science that gets published?
Well, the answer is supposed to be the peer reviewers. These are other scientists who volunteer their time to check over a study before it gets published. But the system is far from perfect, and these reviewers are often caught in a really tough spot themselves.
This editorial we're looking at points out a bunch of systemic problems. For starters, the standards for power analysis can be all over the place from one journal to the next. You've even got some reviewers asking authors to do flawed analyses, like calculating the power after the study's already finished, which makes no sense. And that puts the authors in a terrible position, right? Do you push back and risk getting your paper rejected, or do you just do what they say? And to top it all off, a lot of those older foundational papers that everybody cites, the raw data just isn't there, so you can't even try to replicate their power analysis if you wanted to.
So what's the result of all this? The bottom line is, when these issues slip through the cracks, we're left with a scientific record that's skewed and just hard to trust. This is a huge contributor to what people are calling the reproducibility crisis, this growing problem where scientists just can't get the same results when they try to repeat someone else's study.
Okay, so yeah, it's a complicated problem, I get it. But the good news is, this editorial doesn't just point out all the flaws, it actually offers a really clear path forward. So, how do we fix this? How do we build a stronger, more trustworthy scientific process?
The solutions are actually coming from inside the scientific community itself. And the core idea isn't some fancy, complex new statistic. Nope. It's really just a commitment to two basic fundamental principles: transparency and rigor.
So what does that actually look like? Well, first, authors need to be completely transparent. They need to report all the numbers that went into their power analysis, no hiding anything. Second, they have to clearly justify every single choice they made. No more pulling that 20% dropout rate out of thin air. And third, there's a huge movement pushing for researchers to share their individual level data. That way, other people can check their work and, just as importantly, use that data to plan even better studies down the line.
And this is why all of this matters so much. This isn't just some boring academic debate. There's this really powerful line in the source that just hits the nail on the head. When scientific findings can't be trusted or repeated, it erodes the public's trust in all of science. Getting this stuff right isn't just a nice to have, it's absolutely fundamental.
So at the end of the day, what this all shows us is that science isn't just about what you find, it's about how you find it. The integrity of that process, well, it's everything. And that leaves us with one last big question to think about. If we could actually fix these issues, if we could bring all those well-done but boring studies out of the file drawer, just imagine how much more complete and how much more accurate our understanding of the world would actually be.